In this video, we will talk about the harmonic oscillator in classical mechanics. The term harmonic oscillator refers to any kind of motion where we have a linear force trying to pull the object back to equilibrium. We can describe how things move in classical mechanics by using Newton's laws. In particular, his second law states that in order for a momentum to change, we need a force acting on an object. Since momentum is mass times velocity, we can also write this as mass times the second derivative of x. If we now look at a force which is proportional to x, the resulting motion is called harmonic motion, and the object that moves is called a harmonic oscillator. The most general way to write down an ansatz for such a force is minus kx, which is called Hooke's law. The parameter k determines how strong the force acts, and the minus is necessary to ensure that if we move in the positive x direction, the force pulls back towards the negative. The resulting differential equation is now mx dot dot equals minus kx, or simply x dot dot equals minus k over mx. Now, how do we solve this? Let us first pretend that the ratio k over m is exactly 1, so we don't have to worry about those constants. They are external parameters describing the mass of the object and the strength of the force, so the way how we come to a solution should be independent of those quantities. Now, in this case, the differential equation simply reads x dot dot is equal to minus x. Which functions can be differentiated twice and then be the same again but with a minus sign? The answer is sine and cosine functions. In fact, you can write down an ansatz for the solution in many different ways which are all equivalent. For instance, if the solution would be 2 times the sine of t, then we can adjust the constants accordingly. However, the important thing is that we always have 2 constants, since we are dealing with a second-order differential equation. Depending on where those constants appear, they correspond to different physical properties. For instance, the constants in front of the functions determine the amplitude of the oscillation, whereas the constants inside the function determine the initial phase angles and are called phase constants. These constants a, b, c, d can be determined by initial conditions of the differential equation. But without knowing such boundary conditions, we basically found our solution. Now, back to the case where k over m is not 1. This does not change a lot, we only have to multiply the time with the square root of k over m inside the functions. This way, after differentiating twice, we get back k over m times the negative of the original function. This square root factor is called angular frequency and determines how quickly the object oscillates. To summarize, the amplitude decides how far the object travels from its equilibrium position. The phase constants determine where the oscillation starts, and the angular frequency decide how rapidly the object moves back and forth. This angular frequency usually gets a special name, omega, such that the differential equation reads x dot dot is equal to minus omega squared x. If the mass of the object is large, then omega is small, which means that the oscillation happens slowly. On the other hand, if the mass is small, then omega becomes large and the oscillation happens more quickly. If k is large, then omega is also large, so for a strong force, the oscillation is quick. For a weak force, the oscillation is slow. Finally, there is one more interesting quantity we should talk about. How long does one oscillation take? This is called the period of the oscillation. In order to calculate it, we want that a sine function at some random time is equal to the same sine function after some additional time uppercase t. Since the period of a sine function is 2 pi, we can calculate the oscillation period uppercase t to be 2 pi over omega. This is the same as 2 pi times the square root of m over k. And that's pretty much it for this video. Thanks for watching!